Welcome to physics class on conservation of linear momentum and concurrent forces for class 11. Now in this video class we will try to cover the topics like the relation between the impulse and momentum, that is impulse momentum theory. Next we will try to prove the conservation of linear momentum, and then we will go to the equilibrium of concurrent forces lastly. So let's try to see what is the relation between the impulse and the momentum, rather impulse momentum theory. From the Newton's second law of motion, we know that the external force applied or acted onto a body is directly proportional to the rate of change of momentum. So the more the rate of change of momentum takes place onto the body upon acted by the external force, larger will be the external force acted onto the body. So by changing the momentum, or rather by observing the rate of change of momentum, we can simply say about the external force acted onto the body. If the rate of change of momentum is very large, then the external force acted upon the body must be also very large. Now from here we see that impulse is a product of force and time. Okay, that means impulse is nothing but this is the amount of the force acted onto the body for a very few short duration of time, okay, upon which the force acted onto the body. Okay, the time on which the force is acted onto the body, I mean. So what happened, that external force, this is your Newton's second law of motion. External force is equal to mass into acceleration. Acceleration means what? Rate of change of velocity. So change in velocity, delta v is a change in velocity, and this t is a time duration or time taken, you can say. So what happened, this external force or net force divided by mass, okay, that will be equal to rate of change of velocity, rather this is nothing but acceleration. So if you cross multiply this m to the right hand side, then this t to the left hand side, then what happened, your product of force and time, this will be equal to what? Change in momentum. Delta represents change, okay, mass into velocity means what? Momentum. So your product of force and time, this will give you change in momentum. So F into T, that means force into time taken, is nothing but this is, we call it as impulse, and it is denoted by J. J is a vector quantity, that means impulse is a vector quantity. Why? Because force is also a vector quantity. In some textbook you might seen this representation of impulse by capital I also, okay, that can be done, but this is a matter of notation only, okay. So your impulse J vector, which is equal to what? Change in momentum. Rather this change in momentum is denoted by P, okay. P is a vector quantity, momentum is a vector quantity because V is also a vector quantity. So what happened, this change in momentum, okay, this change in momentum is equal to what? Impulse. That relation between these two, impulse and change in momentum, the relation between impulse and momentum, we call it that as simply what? Impulse momentum theory. So what is that theory? Your impulse is equal to what? Change in momentum. You can write like this. So your change in momentum, that means your change in momentum, it can be denoted by delta p, this is a vector quantity, and this is equal to your impulse, okay. The relation between these two, we call it this as what? Impulse momentum theory, right? So let's see about the SI unit. Now SI unit of impulse is what? Force into time. This is force. SI unit of force is Newton. SI unit of time is second. So your SI unit of impulse will be Newton second. Now let's see about that of momentum. I mean SI unit of momentum. Momentum is what? Mass into velocity. So mass means kg, velocity, SI unit of velocity is meter per second. Okay, so your SI unit of momentum will be what? Kg meter per second. But as we have seen that from impulse momentum theory, that impulse is equal to change in momentum. The SI unit of change in momentum will be also kg meter per second and impulse Newton per second. So impulse Newton per second, okay, and momentum kg meter per second. So you can say that SI unit of impulse is Newton per second, Newton second or kg meter per second. Why? Because your impulse can be related with that of change in momentum. So what happened? Your impulse can either, you can say SI unit of impulse is what? Newton second or kg meter per second. Yes. Let's see. How about a collision? Okay, what happened when two objects collide each other on a level rod? So you consider two objects, okay, speeding toward each other from one from the left hand side, another from the right hand side, and if they collided, then what will happen? Let's see. Due to the Newton's third law of motion, okay, they exert each other and they what happened? Exert each other equal force but in opposite direction. As per your Newton's third law of motion, that for every action there will be equal and opposite reaction, right? So what happened? The two forces interact each other and they collided, okay, when they approach each other, okay, what happened? They will collide it. The time of impact also it will be equal when the force is acted by this second body to the first body. That time of what impact will be also be the time of impact for the other body. That means the time of impact for the two body are equal. Therefore the impulse of the two objects colliding must be also equal. So let's see. From your Newton's third law, what happened? We see that your action is equal to reaction. Minus sign shows that they are equal. Equality shows that they are equal. Minus sign shows that they are opposite. But the time of impact, this is also equal. Okay, so impulse for the first body, impulse experienced by the first body, and this will be equal to what? On the right hand side, this will be the impulse experienced by the second body. Got it? As they are equal and opposite, what happened? The impulse experienced by the first body will be equal and opposite to the impulse experienced by the second body. So as we know that during the collision of the two body, we know that the impulse of the two objects, okay, colliding are equal but opposite in direction. Okay, as I told you that impulse is a vector quantity. So what happens? If it is a vector quantity, it will have magnitude as well as direction. So magnitude will be equal but the direction will be what? Opposite. Got it? So whenever there is no external force acted onto the body, onto the bodies who's taking this collision, okay, then what happen? Impulse will be what? Equal and opposite, right? So let's see about that. If the impulse are equal, then the momentum are also equal. We know that the change in momentum is equal to what? The impulse, right? So what happen? If impulse are equal and opposite, then what happen? Their momentum must be also what? Equal and opposite, right? So impulse is equal to nothing but that will be change in momentum, okay, or change in momentum will be equal to what? Moment, your impulse, I can say. So what is this? Your momentum is what? Mass into change in velocity of the first body. Likewise for the second body also, mass m2, okay, and change in velocity. So let's take it that this v1i, okay, v1i represents the velocity of the first body of mass m1, okay, moving from left to right, and m2 be the mass of the second body of whose velocity is denoted by, I mean initial velocity is denoted by v2i. I just to know it what? Initial, okay. It can be denoted by also what? v02, as it is done here, v02 here. Likewise this v 2I, that is nothing but this is nothing but this is v, okay, initial velocity of the second body. 0 represents what? Initial. 2 represents of that particular body. So VO2 here, it represents nothing but that is V2I, that means initial velocity of the second body. Similarly, V01 here, that is nothing but this is the initial velocity of the first body. Okay, so what happened? Let's see. In the two collision of these two body while approaching each other, let V2I or V02 represents the initial velocity of the second body moving toward the left hand side, and this first body is moving toward the right hand side, that means from left to right, and the second body is moving from right to left, and they collided each other, and the time of collision is nothing but this is small t, and the small t will be same for the two body, okay, as they are colliding with each other. Whatever the time of impact that is happening onto this mass m1, that will be also the time of impact onto this mass m2. So time of collision or time of impact will remain same. From there, what happened? Newton's third law said that for every action there will be equal and opposite reaction. So F into time of impact of the first body, that will be equal and opposite to the F and time, okay, that is happening onto the onto the second body. So what happened? Their impulse will be equal and opposite, right? Impulse is what? Impulse is nothing but that is the product of force into time. So impulse is what? Impulse, now in the previous slide we represent impulse by J, and here it represents by I1, okay, by I. So your first impulse that is experienced by the first body, that will be what? It will be F into T, like this. And for the second body, it will be what? It will be the same force but in opposite in direction with the same time of impact, okay. As the force is equal and opposite, if you are going to write it in the vector form, then what happened? It will be like this with an arrowhead like that. So for this impulse that will be experienced by the second body, the force will be equal and opposite to that of the force experienced by the first body. So the second body, okay, will experience impulse opposite, so we may write that with 1 minus here. That is what it is written here, okay. So F1 will be equal to minus of F2, right? That is what we are having here. So what happened? This change in momentum of the second body, change in momentum of the first body, that means change in of the first momentum of the first body will be mass into change in velocity. Mass cannot be changed, so velocity need to be changed, okay, as momentum is equal to mass into velocity. So likewise here also for the second body, minus of mass of the second body, change in the velocity of the second body, right? So if you do it that one, change in velocity of the first body means what? Final velocity minus initial velocity. This represents your final velocity, V1 F, F for final, okay. Just to make you understand, I just make it as F, I like that, I for initial, F for final. So this is the final velocity of the first body, which is denoted here by V1 alone, and this 0 represents the initial velocity, okay. So final velocity minus initial velocity will give you change in velocity of the first body, got it? Likewise, final velocity for the second body is F, V2F, which is denoted here in this will be equal to your V2 here, okay. This is the final velocity of the second body minus initial velocity of the second body. So this is a change in velocity of the second body. So the product of the change in velocity and its mass will give you change in momentum of the second body. Now if you cross multiplied it, if you transfer it this initial velocity of the second body, okay, or you can take it like this also. From this relation m1 v1 will be there, okay, and this minus v01 is there. So if from this equation if you do like this, then it will be in this way. Similar, this implies that, let me write like this. So what happened? You try to transfer this what final velocity toward the left hand side and this initial toward the right hand side, so that it will be what? V1 m1 v1 m1 v1, okay, plus m2 v2. If you transfer this, okay, to what, left hand side, then left hand side will be equal to like this. This will be equal to what, there onto the right hand side it will be m1 v01 plus m2 v02, like this, right? This is 0, okay, v02. So what happened, this m1 v1 plus m2 v2 is what, this is the momentum, final momentum of the body 1, and this m2 v2 is the momentum, okay, the final momentum of the second body. That means this is the total momentum of the system. System means for these two bodies, okay, after collision. And what is this onto the left hand side? This is the initial momentum of the first body, initial momentum of the second body. That means this is the sum of the initial momentum before collision. So what we can say from this expression is that, okay, momentum after collision is equal to momentum before collision. Okay, so whenever there is no external force, the total momentum of the system before collision is equal to total momentum after collision. So if momentum remains equal before collision, after collision, that means your momentum remains same. In physics we say this same as conservation of momentum. Okay, so we will do that one in the next slide. Okay, now let's see. That is what we are having. Okay, so this is summation, means total momentum. P represents momentum. Okay, total momentum before collision is equal to total momentum after collision. That is what we have just done that one. Okay, now let's see. Let's try to state the principle of conservation of linear momentum, and at the same time we will try to prove it. Okay, according to the principle of conservation of linear momentum, okay, the total linear momentum of the system is constant if the net external force acting on the system is 0. That means if there is no external force acting onto the system, then the total linear momentum of the system remains constant, or you can say conserve. Okay, now to prove this, we can do it in a very short and simple way by using your calculus. But if you want to do it in that of the normal mathematical expression without using the calculus, then you can do it in this way also. So let's try to do it first by using your calculus. Okay, according to the Newton's second law of motion, we know that external force F, okay, vector is equal to rate of change of momentum. This dp by dt is nothing, it represents what, change in momentum divided by change in time. So it denotes what, this as rate of change of momentum. Now we can write it this as what, d by dt of what, p vector, right? Like this. This is nothing but this is the rate of change of what, momentum. When I say rate in physics, always the denominator should be time. So change in momentum to the change in time, we said that as rate of change of momentum. Got it? Now see, in the definition, if there is no external force acted onto the body, right? So what happens if F vector is equal to 0, then your this dp by dt will be equal to what, 0. Got it? But in calculus we know that if a differentiation of a quantity, okay, if a differentiation of a quantity is equal to 0, then that quantity must be a constant quantity. We always say like that, that differentiation of a constant quantity is always 0. So that means differentiation d by dx of, say, suppose y, if it comes out to be 0, Now it may be a vector quantity or may not be a vector quantity. So for us, as it is a momentum as a vector quantity, let's take it as what, a vector quantity like this. If a differentiation of y with respect to x, if it comes out to be 0, then y it must be what, a constant. Got it? So likewise here also the same thing. If the rate of change of momentum is equal to 0, why 0? Because your external force is 0, no external force x onto the body. Got it? So what happened, your rate of change of momentum will be equal to 0. That means your momentum must be what, constant. Okay, like this you can prove it, this one, by using a calculus. If you are asked to prove that the conservation of linear momentum by giving some 2 marks simply, then you can write the statement and the proof like this simply. Okay, so what happened, if you want to do it in the general mathematical way, then you can do in the way it is given here. Okay, consider a system having n particles. That means in that system there are small n particles, and each small particles will have a momentum p1 vector, p2 vector, p3 vector, so on up to pn vector. Okay, that means p1 represents the linear momentum of the first particle, p2 represents the linear momentum of the second particle, and so on. This pn vector will represent the momentum, or rather the linear momentum of the nth particles respectively. Got it? You know, momentums are of two types. One is linear momentum and another one is angular momentum. Okay, angular momentum arises whenever the object is moving in a circular motion or rotational motion. Okay, until and unless stated that it is angular momentum, when I say momentum, it will mean linear momentum only. Okay, so therefore let's see, the total momentum of the system is what, that means total momentum means what, sum of the momenta. Okay, though this total momentum p vector will be equal to what, sum of the momenta p1 vector plus p2 vector plus p3 vector, so on up to pn vector. So if f external be the force acting onto the system, then F external will be equal to what, rate of change of momentum, as it is given by your Newton's second law of motion. So your P vector will be nothing but it will be the sum of the momentum. So if you represent it, this P vector by P1 plus vector plus P2 vector plus P3 vector, so on up to Pn vector, then what happened, you can replace it this external force by 0. Okay, then what happened, the sum of the momentum will be what, constant. As I told you, the differentiation of the sum of momentum is equal to 0, then the sum of momentum will be what, a constant quantity. So in this way also you can prove it. Now let's see about the next one. This one actually we have done this in the case of the lower classes like that of class 9. We did it this one. Okay, but still for your understanding, let me do it here. Okay, derivation of law of conservation of linear momentum. Okay, using your Newton's third law of motion. Now let's take it that these two objects A and B having masses m1 and m2, okay, moving with initial velocity u1 and u2 respectively on a level surface. Okay, with that, what, this u1 vector must be greater than u2 vector. Okay, as these two objects are moving along the same straight line in the same direction, let these body A and body B collided somewhere after traveling for some distance. Okay, so in order to collide it, what happened, the body which is moving behind must be having more velocity than that of the forward body. Got it? So what happened, u1 must be greater than u2. So what happened, after moving for some distance, then what happened, this mass, okay, m1, or the body A having mass m1 will surely collide with the body B of that of mass m2. Okay, in order to have that collision, we need to have this condition essential, that initial velocity of the body A, that means u1 must be greater than u2. So when they collided, okay, let the two bodies I mean continue to move in that particular direction along the positive x-axis. Okay, so what happened after collision, let the velocity of the two body be v1 and v2 respectively. That means for the body A, let the velocity of the body after collision be denoted by v1, and v2 vector represents the velocity of the body B after collision. So this the diagram or a figure is for the two objects before collision, and this is the diagram for the two body during collision. During collision, what happened, they will interact it and the time of impact or collision will remain same. Okay, if t is the time of impact for the first body A, then that same time will be also the time of impact for the second body B. So after collision, they will separate it like this, with moving with different velocities v1 and v2 respectively. Okay, so what happened if you try to find out that the momentum of the system before collision, that means mass into velocity, m1 u1, m2 u2, that will be the momentum for the second body, product of mass, and the velocity will be the momentum of this body. So what happened, the total momentum of the system before collision will be what, m1 u1, it is written here, m1 u1 plus m2 u2, right? Similarly, total momentum after collision will be what, mass into v1 plus m2 into v2, that is what it is written here. Okay, try to remember it. Okay, this m1 is moving with initial velocity u2 and u1, and m2 is moving with velocity u2 vector. After collision, what happened, the two body moves along the same direction with the velocity v1 for the body A and with the velocity v2 for the body B. Now let's see, change in momentum of the body A. Change in momentum of the body A means what? Final momentum minus initial momentum of that particular body. Now as this body A moves with a velocity, final velocity after collision, it moves with what? v1, and that body B having m2, that moves with body with the velocity what? v2, right? So what happened, this, let me remove it out. Okay, that will be better, I think. So what happened, this m1 and v1 is the final velocity, final momentum of the body A, initial momentum of the body A. Likewise, m2 v2 is the final momentum of body B, m2 u2 is the initial momentum of body B. So change in momentum, okay, for the body A will be expressed like this. Similarly, for that of the body B will be expressed in this way. So during the collision, the body exerts a force FAB on body A. That means this is the force, okay, experienced by the body A due to the body B. That means body B exerts on to the body A, and that will be represented by FAB vector. What is this actually? This is the force experience or felt, okay, felt, you can say, the force experienced or felt by the body A due to the collision of body B onto A. Okay, you can take it in that way. That will be equal to what? FAB and FBA. Okay, there are two forces here. One is FAB, that means the force experienced by body A due to body B, and this is FBA, which is the force experienced by the body B due to the body A. That means the body A collide onto the body B, and body B experience a force, and that force denoted by what? FBA represents what? Force experienced by the body B due to the body A. But from Newton's third law, we know that action, if one is taken as action, the other will be reaction. If you take it this as action, this will be equal to what? Reaction. We know that from Newton's third law of motion, that action and reaction are equal and opposite, okay. So it will be replacing this FBA and FAB from here, and if you replace it those things here, and after transferring those of the initial momentum of the two body onto one side, final momentum onto the other side, then you will get it that the sum of the momentum of the two body before collision, rather this is a momentum, initial momentum, before collision of the first body, and this is the initial momentum of the second body before collision, and onto the right hand side this is the momentum, the final momentum of the body A, after collision, and this is the final momentum of the body B after collision. So we know that from the last equation that this is the sum of the momenta of the two body A and B before collision, and this onto the right hand side is the sum of the momenta of the two body A and B after collision. That means the sum of the momentum before collision is equal to the sum of the momentums of the two objects after collision. That means momentums remain same. There is no change in the momentum before collision and after collision. It means what? It is also given here, momentum of an isolated system. Isolated system means no external force acted onto the system, It means that momentum of an isolated system before collision is equal to momentum of an isolated system after collision. This is a law of conservation of linear momentum, and it is stated as, if you want to give the statement, then this will be the statement for the conservation of linear momentum. For an isolated system, the total vector sum of momenta of the two bodies remains conserved and is unchanged due to the internal forces of the system. That means action and reaction. Internal forces means forces among the particles, or among the two bodies, but there is no external forces acted onto the body, either onto the body, first body, or to the second body. There is no external force. Whatever the force that arises, that are nothing but that are the internal forces. That is what we are saying about that, what this action and reaction. This action and reaction are nothing but these are the internal forces, Now let's see about the graphical method for measurement of impulse. When a force acted onto the body is a constant force, then if we can find it out, the graph between the force and time, force along the y-axis and time along the x-axis, because time is an independent quantity and your force is a dependent quantity. The amount of force acted onto the body depends upon the time. So what happens if you draw a graph of that force versus time graph, then the area under this graph will represent what? Your impulse, force into time, right? Force into time means what? This impulse, either you can represent it by I or J. This will be equal to what? Force into time, right? So if you take it only the magnitude, then we need to take it modulus like this. So this is what? Force into time. So force at this time, what happened? Force is this much. Got it? Force is this much. At this instant of time, force is here. Got it? So if you want to find out the impulse, then the area under the graph means this area. Got it? The shaded area will be numerically equal to the impulse experienced by the body. Got it? So we have to say that like this. From the graphical representation, we can find out impulse. From where? From the graphical representation means from the force time graph. So the area under the graph of this force time will numerically be equal to the amount of impulse that is experienced by the body. That is what I have written here. You try to pause the video and you can note down. And let's take it to the next one, which is due to a variable force. Suppose if a body is acted upon by a variable force, then how we will find the impulse from the force time graph? Let's see. This is about that of the variable force, and this is the graph of that force versus time graph. Okay, let's see. Let me a little bit zoom in, okay, so that you can see it. Now this is the time axis and this is y-axis. Okay, along this y-axis you try to draw force, and if the graph of that force versus time graph is like this, then what happened? We need to divide this time into small durations. Okay, so that what happened, at that small interval of time we may assume to a fair approximation that the force remained constant. Okay, now what happened if you are going to take it that the force is going to be constant? That means if you are taking your time duration very small, that means your AB, okay, this length AB will be very close to each other. If I take it that A and B are very close to each other, then this if you take it this time as delta t, okay, I mean the distance between this time A and B, if it is very small, then what happen, your point B and C will be also very close to each other. That means if you try to find out at the very beginning of this delta t, the force will be represented by this point. Let's take it this point, okay, here. And if these two, that means A and B, are very close, that means your this D and C will be also very close. And if you try to find out the force at the end of this small duration of time delta t, then what happened? These two forces, one here at this point, another here at this point, this will be very close to each other. And to a fair approximation, we can take that these two forces are same. Okay, if you take it that these two forces are almost same, then you may apply that, okay, graphical representation to find out the impulse, okay, for a constant force. Then for that constant force, we know that the product of the force and time, we know that that will give you impulse. So graphically we know that the area under the curve of the force time graph will represent what? The impulse. So this small strip will represent the impulse for that small duration of time. Got it? So if you try to divide it, these graph into small durations of time, okay, like that, then there will be so many strips here, right? So if you try to find out the area for such small strips, then you will get it the impulse for that small strips. Suppose if you want to find out impulse from here, from this very beginning up to this time, then you need to find out the area under this graph. Okay, under this graph means from here to here. Okay, this area under the graph can be obtained by adding these small strips together. So that will give you the amount of impulse from this time to this time. Okay, likewise you can do it for whichever whatever time you want to find out the impulse, you can easily find out in this way. Got it? So let's see in the next. Here the description is given here. The description is very lengthy. I have given you all the descriptions here so that you can read it and you can understand it more. Okay, whatever I have already explained, it will be in this description. Okay, try to pause the video and try to read it. Okay, now in order to save time, let me switch on to the next slide. Okay, now this is about that of the concurrent forces. What is meant by concurrent forces? Now if two or more forces acted onto the body, and if the line of action of these forces intersect at a point, then those forces are known as concurrent forces. Can you get my point? Now onto an object, okay, let me draw the diagram here. Onto an object like this, let's take it an object like this. There are some forces acted onto the body like this, okay, in this way. And if these forces denoted by F1, F2, F3, so on, F4, F5, so on up to Fn. And if these forces acted onto the body, and if their line of forces, okay, line of forces, okay, when they produce it, if they intersect at a point, then these forces are known as concurrent forces. For example, if there are three forces here, one is F1 denoted, okay, by F1, another is F2 here denoted by F2 vector, another force is here denoted by F3 vector. And if these three vectors, okay, when they produce it, then what happen? If they intersect at a point here, then these forces are known as concurrent forces. Suppose one force here, another force here, another force here, like this, and if they produce it, okay, then, and if they intersect it at a point, then these three forces are known as what? Concurrent forces. That is the meaning. Okay, line of action means when you produce it, a force is here. That means the line when you produce it, okay, both sides, toward this side or toward that side, doesn't matter. When you produce it, that line, we call it as line of action of the force. Got it? Yes. So what is the condition for the equilibrium of such concurrent force? Let's see. Now, if these concurrent forces, okay, acted onto the body, if they are going to be in equilibrium, then upon acted upon by these concurrent forces, the body should be at rest or at uniform motion. Got it? If it is uniform, means what happen? Upon acted upon by these forces onto the body, if the body keeps on moving with a uniform motion, then upon acting by these three forces or four forces, I mean concurrent forces, the body will still continue to move in that equilibrium, or what? In that constant uniform motion. And if the body is at rest, then what happen? Upon acted upon by these concurrent forces, the body will still continue in that state of that rest. Got it? So the condition, I will not read it out all, but you try to read it, okay? But I'm telling you that if the body, okay, or the concurrent forces, okay, upon acted to a body, what happened? The body will be in its initial state. If the body is in uniform motion, okay, when acted upon by these concurrent forces, the body will still continue to move in its uniform motion. If the body is at rest and upon acted by these concurrent forces, the body will still continue in the state of rest. Got it? Suppose if it is one is at rest, this is in rest, another is moving with what? Uniform motion. That means let's take it that with a constant initial velocity u. And if this body which is at rest, if it is acted upon by these three forces, okay, one along here, another along here, another along here, let's take it that this is one F1, this is a second force, and this is a third force. So what happened when these three concurrent forces, okay, in order to say that these three forces are at equilibrium, what happened? Upon acted on to these forces, okay, to this body, these three forces will be equilibrium only when the body will continue in its initial state of rest. Okay, if it is not equilibrium, then what happened? This body will start moving or changing its position. Okay, then what happened? The condition is what? The sum of, or rather the algebraic sum of these three forces, F1, F2, F3, this will be equal to what? 0. This will be equal to 0. That means what happened? These three forces can represent, okay, the three sides of a triangle, taken in order. Okay, only when these three forces, okay, if these three forces can represent both in magnitude and direction by the three sides of a triangle taken in order, then what happened? This will hold good. Got it? That means the sum of these three forces will be equal to 0. If it is equal to 0, then what happened? The three forces are said to be in equilibrium. That means the concurrent forces are in equilibrium. If they are in equilibrium, upon acted by these three forces onto a body, the body will continue in the state of its state of what? Rest. If the body is moving with uniform motion, upon acted by these three forces, then the body will continue to move in its initial state of what? Uniform motion. Got it? If the body is at rest, upon acted by the concurrent forces, it will be equilibrium only when the body which was at rest will continue to be at rest. Okay, and the condition for equilibrium of the concurrent forces on acted upon onto a motion which is moving with uniform motion, that means constant initial velocity. It will move with constant initial velocity upon acted upon by these what? Three forces. If they are not equilibrium, then what happens? It will not be continuing in its uniform motion. Either it may be accelerated or decelerated, or either it may be changing its direction. Okay, yes, that is what. Okay, so what happened? The condition for equilibrium of the concurrent forces is that the forces acted onto the body may be or can be represented both in magnitude and direction by the polygon taken in order. Okay, suppose why I am saying polygon instead of triangle, because if there are more than three forces, concurrent forces acted onto the body, then what happened? Those forces can represent both in magnitude and direction by the what? Sides of a polygon taken in order. Got it? So that is the condition for equilibrium of concurrent forces. Mathematically, you can say that the algebraic sum or vector sum, it is having the it carry the same meaning. Either you can say that the algebraic sum of the forces, or the algebraic sum of the forces, or the vector sum of the forces must be always equal to 0. If the algebraic sum or vector sum of all the forces acted onto the body is equal to 0, I mean the forces, concurrent forces is equal to 0, then that will be the condition for equilibrium of those concurrent forces. Got it? Had there been four forces, then what happened? The sum of f1 vector plus f2 vector plus f3 vector plus f4 vector must be also equal to what? 0. That is the condition for equilibrium of concurrent forces. Got it? So with that, we will try to come to the end of our today's class. Thank you for watching my video.